There was no bang, no thunderclap across a silent void, no eruption from a cosmic fuse, no light, no sound, no space for them to even exist. What we call the Big Bang is one of the greatest misnomers in human history. It wasn't an explosion in space. It was the birth of space. It didn't detonate into emptiness. It whispered time into existence. The Big Bang wasn't the firework. It was the match. Please like and subscribe because this journey will change how you see our place in the universe. Prepare yourselves. We begin. We imagine it like we imagine all beginnings sudden, violent, loud. But the universe didn't emerge from nothing with the force of a bomb. It unfolded from itself. It began everywhere at once. Every point in space, every atom in your body, every distant star and forgotten void all trace back to the same moment. A single tick, not on a clock hanging somewhere in space, but the invention of time itself. Let that land for a second. The Big Bang didn't happen in the universe. The Big Bang is the reason the universe can happen at all. Imagine you're holding a ruler. Now imagine a clock. The Big Bang is not the first inch on the ruler. It's the first second on the clock. It didn't come from a place, it birthed place. It didn't come from a time, it became time. So when you ask, where did the Big Bang happen? The answer is both nowhere and everywhere. It happened in the room you're sitting in now. It happened in the center of your chest. It happened in the empty space between galaxies and in the dust inside a dying star. The universe didn't begin from a point. The universe began as a point without size, without volume, but brimming with possibility. This is the paradox at the heart of everything. Scientists call it a singularity, a moment where equations stop making sense, where density becomes infinite and space vanishes. But that's not a destination. That's a failure, a sign that our math, or logique, our physics break down at the edge of reality. The singularity isn't a thing. It's a shadow, a question mark drawn in cosmic chalk. We don't know what was there. We only know what came after. The universe, once smaller than the smallest thing you can imagine, began to swell to stretch. Not into space, but as space. There was no outside, there was no before, there was only this moment, this unfolding from impossibly hot to merely scorching, from smooth to structured, from empty of atoms to overflowing with galaxies. Every breath you've ever taken was made possible because of that quiet surge, and it didn't roar, it expanded. We call it the Big Bang theory, but there was no bang. The name was coined mockingly by astronomer Fred Hoyle, not to explain, but to ridicule, and yet the name stuck, even as the science evolved, because what followed was too vast, too beautiful, too mysterious to be reduced to a single syllable. The truth is more poetic, more subtle. The Big Bang was not an explosion. It was a blossoming, a flower of fire, unfolding in every direction of time and space, and it's still unfolding. Right now, around you, inside you, you see, the universe doesn't have a center, it doesn't have an edge. It expands not from a place, but from itself. Every galaxy is running from every other galaxy, not because they were blasted apart, but because the stage they rest on, space itself, is stretching beneath their feet. Like raisins baked into a rising loaf of bread. We drift apart not because of momentum, but because of the dough, because of the space expanding between us. So if you travel far enough in any direction, you won't find the edge of the universe. You won't hit a wall or a boundary. You'll just find more universe, more stars, more silence, more mystery. And that, too, has a lesson. The cosmos is not a place we're in. It's something we're part of, a thing we carry within us. And now, a deeper mystery. If the universe had a beginning, Does that mean there was a before? What was there before space and time? What could exist before existence? These aren't just scientific questions. They're philosophical wounds, open spaces in our understanding, aching to be filled. Because if everything we are came from the Big Bang, the atoms in our bones, the iron in our blood, to the stardust in our breath, then what came before the bang is what came before us. And yet, we may never know the singularity, if it even existed, lies hidden behind a veil. We cannot pierce a veil made not of smoke, but of math, a wall where equations loop back into themselves like snakes devouring their own tails. This isn't a flaw in the universe, it's a flaw in our vision, but in that blindness is opportunity, because it's here, in the shadows of our ignorance, that new ideas are born. This is not just science, it's story, it's mythology, it's a human attempt to describe the indescribable, to trace a map of a territory we can never fully see. The Big Bang is not just a theory, it's a mirror. It shows us not just where we came from, but how little we understand about why there is something rather than nothing. We were not given an answer. We were given a beginning, and from that moment forward, the universe has been writing a poem in space and time, a poem we are only just beginning to read. And that poem began not with a bang, but with a breath. What came before the universe? It's a question that lingers like smoke after a fire, tempting, haunting, and perhaps impossible. Because to ask what came before the Big Bang is to invoke a kind of heresy in physics. It is to imagine a time before time. But what if there was? What if the clock of the cosmos wasn't the first ticking thing, but simply the first we can hear? The Big Bang is not just the birth of particles and galaxies and expansion, it's the birth of time itself. If the universe had a beginning, then so too did time. That's what our equations say, or, more truthfully, that's where they fail. The moment we push past that first Planck time, that infinitesimal instant after the Big Bang, the math breaks down. We stare into a wall of infinity. Equations return nonsense. Logic folds in on itself like paper crushed in a fist. We call that wall the singularity. Not because we understand it, but because we don't. A singularity is a placeholder, a confession. It says, here, our knowledge ends, but behind that veil lies something even more mysterious than space or time. The silence before sound, the void before thought, the place where the laws of physics, so carefully written across the sky, begin to unravel like loose threads from a cosmic tapestry. So we ask again, did time begin, or did it only begin for us? There are those who suggest our Big Bang wasn't the beginning at all, merely a transition, a rebirth, a turning of the cosmic page. They point to the expansion of the universe as a clue. Everything we observe suggests that the cosmos is still growing, stretching into an unseen future. But could there have been a collapse before the expansion? Could there have been a universe that fell inward, crushed by gravity, only to bounce back into ours? Others turn to quantum fields, invisible oceans that permeate all of reality, and wonder if one of them stirred, fluctuated, and spilled over, creating not just a burst of energy, but the very framework in which energy could exist. In this view, there was something before the Big Bang, but not anything we'd recognize. No space, no time, only potential, only possibility. But here lies the paradox. To speak of before the Big Bang is to rely on language shaped by time. Our minds evolved to understand sequences, progressions, befores and afters, causes and effects. It's how we live, how we remember, how we survive. But the Big Bang didn't happen in time. It invented time. So to ask what came before is like asking what's north of the North Pole. The question dissolves. The compass spins. There is no before, because before has no meaning in the absence of time. And yet, that's not satisfying, is it? We don't want to believe in edges, in endings, in mysteries that tell us to stop asking questions. So we keep asking, and in that stubbornness, we find new doors. Modern physics offers many of those doors, some open to strange rooms filled with colliding branes, multidimensional membranes floating in higher dimensions, crashing into each other and igniting universes like sparks from flint. Other doors open to the cyclic model, where our universe expands, dees, and is born again endlessly. Like a cosmic heartbeat, some physicists see the universe as eternally inflating, forever budding new realities in a multiverse that never stops growing. In that view, the Big Bang is just a local event, one bubble in an ocean of bubbles. And then there are theories, like loop quantum gravity, which suggest the universe can't shrink to a singularity at all, that instead of collapsing into nothingness, it reaches a smallest possible size and then bounces back. The big bounce, not the Big Bang. In this view, time has always been there, but like a tide, it recedes and returns. The past isn't a line stretching infinitely backward, but a wave crashing, retreating, repeating. But each of these ideas shares one feature. They try to preserve something before the beginning. They refuse to accept absolute nothingness. Why? Because nothing is harder to explain than something. Because even emptiness is not truly empty. Because nothingness, in the physics we know, is unstable. Quantum mechanics, that strange, beautiful theory governing the smallest things, tells us that even a perfect vacuum isn't truly empty. It teems with fluctuations, temporary sparks of energy, particles and antiparticles blinking into existence and vanishing. This is the quantum foam, the restless sea beneath the smooth surface of space. And from this chaos, it is conceivable, perhaps even inevitable, that a universe could emerge, that what we call nothing is, in fact, the raw material from which everything is born. But now we're in dangerous territory, because if even nothing can give rise to everything, we're left with another haunting question. Why? Why this universe? Why these laws? Why is there something rather than nothing? Why is the void fertile? Why does existence exist? And here, again, we encounter our limits, not of imagination, but of language, of logic, of what it means to ask a question. Because the origin of the universe may lie beyond the reach of experiments, beyond the reach of our tools, perhaps even beyond the reach of thought itself. What do you call a beginning when there's no time for it to begin? What do you call a cause when causality itself hasn't been born? The Big Bang is a threshold. On one side, there is physics, observation, mathematics, the great triumphs of human thought. On the other side, there is silence, not the silence of ignorance, but the silence of the unspeakable. We stand at that threshold, peering into the darkness, trying to name what came before the light, and maybe, just maybe, the question isn't what came before the universe. Maybe the question is, why do we need a before at all? 13 billion years ago, the universe screamed, and that scream still echoes, but it's no longer sound. It's light, faint, cold, stretched by time and space into microwaves, a whisper from a fire that has long since cooled, a fossil of radiation, glowing not in brightness, but in memory. This is the cosmic microwave background, and it is the afterimage of creation. Let's go back not to the singularity, but to a time when the universe was still young, not even a second old, a storm of raw energy. Matter hadn't formed, light couldn't travel, it was too hot, too chaotic. The cosmos was a thick soup of particles, slamming into each other with relentless fury, but then cooling, not like tea left on a table, more like destiny unfolding. As the universe expanded, temperature dropped, and after 380,000 years, something incredible happened. Light was freed, atoms formed, photons, particles of light, were no longer trapped in a prison of chaos. They could move, travel, escape, and they have been traveling ever since. That light is still here, all around us, not in beams or bursts, but as a uniform background radiation bathing the cosmos in a cold, ghostly glow. We can't see it with our eyes, but we can measure it, and when we do, we find something extraordinary, a map of the infant universe. In 2013, scientists gathered in the historic halls of the Paris Observatory. It was a celebration, but not of a launch or a discovery. It was a celebration of clarity. They had just received the most precise image ever taken of the cosmic microwave background. The data came from the Planck satellite, a mission that had spent years scanning the sky, pixel by pixel, assembling a picture not of stars, but of the universe itself when it was a baby. And the image was beautiful, not in color or complexity, but in truth. It showed tiny fluctuations in temperature, mere millionths of a degree. But those fluctuations weren't noise. They were the seeds of everything. Galaxies, clusters, stars, us. These tiny ripples in the early universe would grow, pulled together by gravity, over billions of years, into the vast web of cosmic structure we see today. The champagne bottles at that celebration weren't just adorned with logos or stars. They were wrapped in that image, a map of creation itself, printed on glass, because for the first time, we had confirmed with stunning precision that the story of the Big Bang was not just a theory. It was etched in the light of the cosmos. But this discovery revealed something else. Something even more profound. The light wasn't uniform. It had structure, geometry, patterns, and those patterns matched predictions from an idea that had, until then, seemed speculative. Cosmic inflation, the idea that, in the earliest fraction of a second, the universe exploded in size. Not slowly, not gradually, but exponentially, growing faster than the speed of light, inflating from subatomic to cosmic in less than the blink of an eye. It was a mind-bending concept, one that solved many problems like why the universe looks so smooth, or why it appears so flat. But it was also deeply strange, and yet the cosmic microwave background supported it. The data lined up, the numbers sang, that faint glow, that hum of ancient photons told a story, not of a single bang, but of a universe swollen by something more powerful than fire. So what is this inflation? It's not an explosion, but a transformation, driven by a scalar field, a kind of energy that fills space like a fog, everywhere at once, invisible and potent. This field, in its earliest moments, was high in energy, but something changed, a shift, a collapse, like a ball rolling down a hill. It dropped to a lower state, and that drop released enormous energy. The result? Space expanded by a factor of 10 to the power of 50 or more in less than a heartbeat. And with that expansion, the structure of the universe was set. The quantum jitters, the microscopic fluctuations in this inflationary field, were stretched across the cosmos. They became the temperature variations we now see in the microwave background. And those variations became us. Think about that. Your atoms, your body, your memories. They are the echo of quantum ripples, written into the early universe and magnified by inflation. What you are was once a wrinkle in a field that no longer exists. That's not poetry, that's physics. The success of this theory, the match between its predictions and the Planck data, was so precise, so statistically significant, that it left cosmologists stunned. The scalar spectral index, a number that describes how the temperature fluctuations behave, came out to 0. 962. Exactly what inflation predicts. Not a round number, not a guess. A cosmic fingerprint. It was a moment of celebration, but also of awe, because this meant the story we told about the universe beginning in a hot, dense state, expanding, cooling, forming atoms and galaxies wasn't just plausible. It was written in the sky, and that sky is still glowing. Even now, if you tune an old television to static, a tiny fraction of that fuzz is from the microwave background. The birth of everything buzzing through your living room. We live in a universe that remembers, that speaks to us, not in words, but in radiation, in energy, in structure. The light that surrounds us isn't just starlight. It's the fossil of fire, and in that fossil is written the truth. The Big Bang may not have banged, but it burned, and it left a trail, a cosmic breadcrumb path, leading us back to the moment when everything we know and everything we are was still light. The early universe was not born in balance. It teetered on a razor's edge of chaos and possibility, and at the center of it all was something we still don't fully understand. A field, not a field of grass or wheat, but a scalar field, the most primitive kind of field known to physics. No direction, no spin, just a number, a value at every point in space. It existed before the particles we know, before photons danced or gravity curved. This field didn't light the universe. It inflated. It blew it up from subatomic to cosmic in a fraction of a second. And when it was done, it left behind everything. In 1979, a young physicist named Alan Guth stared at a problem. The Big Bang, as it was understood then, predicted a universe filled with defects, cosmic scars, monopoles, strings, and strange warps in space-time. But the sky was silent. The defects weren't there. Why? Guth had a thought, a speculative, almost disparity idea. What if, in the earliest moments, the universe grew too fast for defects to survive? Imagine inflating a balloon so quickly that dust never gets a chance to settle on its surface. The imperfections get blown away, beyond the observable, out of reach. This idea became known as cosmic inflation, but it needed a fuel source, a mechanism, a trigger, and so Guth proposed a scalar field, one that held immense energy, like a compressed spring stretched to its limit, and then it snapped. This field, sometimes called the inflaton, existed everywhere, a constant sea of potential, and then, as if rolling down a slope, it dropped into a lower energy state. That transition released an unfathomable burst of energy, not in a burst of particles, but in an expansion of space itself. The universe didn't grow. It exploded in size. In less than 10 to the power of -30 seconds, it went from smaller than an atom to larger than a galaxy. Not because matter moved, but because space stretched faster than light could keep up. This isn't science fiction. This is the mathematics of space-time itself. And in that rush, that silent calm, incomprehensible surge, the structure of everything was written. But that was only the beginning, because after the inflation ended, the universe was cold, empty, vast. It needed to be reheated, and that's where the magic of scalar fields shows its full potential. As the inflaton field settled into its lowest energy state, it didn't stop. It oscillated like a bell that keeps ringing after it's struck, and in those oscillations, energy was transferred back into the fabric of reality, not as expansion, but as particles. This is the moment when everything we know was born. Electrons, photons, quarks, neutrinos, even the dark matter we still don't understand, all emerged from the death throes of a decaying field. It's a creation story with no divine hand, no cosmic sculptor, just a field rolling down an energy curve, reshaping reality by the rules of quantum theory. Let's pause here, because the implications are staggering. If this story is true, and the evidence grows stronger every year, then the most violent transformation in the history of the cosmos wasn't an act of destruction, but a gentle fall, a field lowering itself, a cosmic transition, quiet but potent. This is how inflation solves some of the greatest riddles in cosmology. Why is the universe so smooth? Because before inflation, everything was close enough to even out like water in a pan. Then space expanded, locking in that uniformity across unimaginable distances. Why does space appear flat? Because when something becomes enormously large, it always seems flat up close. Just like the Earth feels flat under your feet. Why don't we see the defects predicted by early models? Because inflation scattered them beyond the observable universe. Like sparks lost in a storm, inflation didn't just set the stage. It wrote the rules, but here's the twist. While the idea of inflation is elegant and powerful, it remains in many ways a mystery. We don't know what the inflaton field really was. We've never seen it. It might be gone. It might still linger. Quiet and undetectable. A ghost of creation. We don't know why inflation lasted as long as it did, or why it ended in just the right way to reheat the universe, or why it had the perfect properties to seed galaxies, stars, and minds. It seems finely tuned, Precedes, suspiciously perfect, almost chosen, but chosen by what? A mechanism? A deeper law? Or chance itself? Dancing through quantum chaos? This is where inflation, despite its successes, starts to blur the line between physics and metaphysics. Because if the scalar field could have behaved slightly differently, then the universe would have emerged very differently. Or not at all. And if inflation can occur once, why not again? What if it never really ended? What if new universes are constantly being born, each from their own inflating fields, rolling down their own slopes, igniting their own big bangs? This is the idea of eternal inflation, the seed not just of a universe, but of infinite universes, a multiverse, a new cosmos, separated by unimaginable gulfs of inflating space, unreachable, unseeable but real, and all of it born from the simple behavior of a scalar field. So the next time you look at a flame, remember, the universe wasn't born in fire, it was born in stillness, in the fall of a field, in a gentle tumble that transformed nothing into everything. The Big Bang wasn't the bang, inflation was. The universe did not begin with order, it began with trembling, with fluctuation, with chaos encoded at the smallest scale, the whispers of a reality that had not yet taken shape. And yet, from that trembling, something miraculous happened. Structure, galaxies, stars, planets, people, not imposed from above, but emerging from the very randomness at the universe's core. In the smallest scales of existence, reality becomes strange. Particles exist in multiple places at once. Energy fluctuates spontaneously. Things appear and disappear without warning. This is the realm of quantum mechanics, a framework where uncertainty is not a flaw, but a fundamental feature. It is in this strange bedrock, the quantum foam beneath everything, that our story now continues. Because the early universe, in those first silent moments after inflation, was not smooth. It was speckled, patterned, uneven. And those tiny uneven spots, those random jitters of the inflaton field, were stretched across the sky during inflation. Expanded from subatomic to cosmic scale, they are the fingerprints of quantum fluctuations made colossal, and they became everything. Imagine it tossing pebbles into a vast, still ocean. Each pebble sends out ripples. Some cross, some grow, some fade. Now, imagine those ripples frozen in place, stretched until they cover galaxies, until they span the very sky. That's what inflation did to the quantum foam. It froze randomness into the fabric of space, and those ripples became gravitational fingerprints, slight increases or decreases in density that would, over billions of years, Draw in matter, where the density was a bit higher. Gravity won, atoms gathered, stars were born, galaxies spun into spirals. Where it was lower, space remained empty, dark. Still, the entire structure of the cosmos, the great cosmic web of galaxy clusters and voids, is a reflection of microscopic randomness scaled up by the breath of inflation. This is not metaphor. This is observation, the cosmic microwave background. That faint afterglow of the early universe contains these very fluctuations. It's not perfectly smooth. It's dotted with tiny variations in temperature. And when cosmologists measure those variations, they find something astonishing. They match precisely what inflation predicts. Inflation says there should be slightly more large fluctuations than small ones, a pattern known as the scalar spectral index. In 2013, the Planck satellite measured that index with exquisite accuracy. 0.962, not exactly 1, not uniform, just slightly tilted, just enough to allow galaxies to form. It was confirmation of a cosmic truth. The universe is the result of quantum noise, frozen by inflation and sculpted by gravity. Pause with that for a moment. The stars that light up your sky, they exist because of fluctuations in a quantum field over 13 billion years ago. Your body, your thoughts, your memories all trace back to a moment when uncertainty was etched into space. Randomness didn't just survive the Big Bang, it built the world. But this leads to a strange idea. If quantum fluctuations can give rise to structure, then perhaps they also give rise to difference, not just between stars and galaxies, but between entire universes. This is one of the most startling implications of inflation, because if quantum fields fluctuate differently in different regions of space, and if inflation causes space to stretch faster than light, then each region becomes its own bubble, separated forever from the others. Each bubble has its own initial conditions, its own energy, its own story. Some bubbles evolve into universes like ours. Others collapse. Others expand eternally. Others exist in total darkness, devoid of atoms, stars, or time as we know it. And so from quantum fluctuations, not just structure, but multitude, a multiverse, born not of fantasy, but of mathematics. Yet even if we set the multiverse aside, the power of quantum fluctuation remains. It reminds us that the universe does not require perfection to thrive. That imperfection is creative. That randomness, often feared, often misunderstood, is not chaos, but potential. The seeds of reality were not planted by design, but by possibility, and possibility, amplified by inflation and sculpted by gravity, gave us everything from the spiral of galaxies to the curl of your fingertips. In a way, we are the echo of noise, but not meaningless noise, purposeful, potent, a cosmic jazz, unpredictable, but harmonious. And the beauty of it is that this structure, this web of galaxies and life and consciousness, is the natural outcome of physics. We don't need to invoke divine blueprints. The laws of quantum mechanics, combined with inflation, are enough to write the symphony of the stars. Still, it humbles us, because if our reality was seeded by quantum jitters, then somewhere else, perhaps endlessly, other jitters wrote other songs, other ripples, other galaxies, other versions of you. This is the strange poetry of quantum fields. From the same rules come infinite variation, not chaos, not order, creative uncertainty. So the next time you look into the night sky, remember this: the stars are not just ancient light, they are the crystallized memory of a field that once shook, a field that fluctuated, a field that breathed, and in that breath, the universe was written not as a plan, but as a probability. And you are one of the outcomes. The story of the universe may not be a story at all. It may be a verse, a single line in a much larger cosmic poem, and surrounding that verse, unseen and unreachable, are countless others, universes, realities, entire existences with their own rules, their own fates, their own fires of creation. This is not science fiction. This is the natural consequence of a single idea. What if inflation never ends? We've seen how inflation, this sudden, silent, exponential expansion of space, explains the smoothness of our universe, the seeds of structure, and the cosmic microwave background. But what if that process keeps going? What if the field that powered inflation doesn't stop everywhere at once? What if it ends here, but keeps inflating there? In this model, called eternal inflation, the cosmos becomes an unstoppable engine of creation, birthing pocket universes endlessly, each in its own bubble of reality. Each bubble expands, each one is unique, each one is forever isolated by the very inflation that created it, and ours is just one of them. Picture this, an infinite foam, bubbling with universes, some bubbles small, others vast, some cold, others too hot for atoms, some governed by familiar physics, others by strange laws beyond comprehension. They are born, swell with particles, and fade into silence or burst into stars. They never touch, they never cross, they are too far apart, separated by inflating space that expands faster than light can bridge. It's a cosmos so large, so teeming with variety, that everything that can happen does happen somewhere, not once, but endlessly. This is the multiverse not as metaphor, but as mathematical inevitability, and it all begins with the nature of the inflaton field. In quantum physics, no field evolves smoothly. There are fluctuations, deviations, randomness. So as inflation proceeds, tiny regions fall out of it. The field decays there, creating a universe, but elsewhere, the field fluctuates upward, delaying the decay. Inflation continues in those regions, and while they inflate, they spawn more bubbles, and so the process repeats forever. It's like a fractal, a tree whose every branch grows new branches, endlessly, or like a fire that spreads faster than it can be extinguished. This isn't speculation. This is what the mathematics of inflation predicts. And if this is true, then our Big Bang was not the first, and it won't be the last. It was simply the inflation field, in this region of space, collapsing, giving birth to time, matter, light. Elsewhere, the field still inflates. Elsewhere, new universes are being born. Even now, this is what eternal means. Not just a long time, but never ending. But eternal inflation comes with a price. We are no longer the center of anything. Not spatially, not philosophically, not cosmologically. Our universe is not special, not privileged, not handcrafted. It is one bubble in a sea of bubbles, a raindrop in a storm, a verse in a song too vast to be sung. Some physicists find this beautiful a celebration of nature's creativity. Others find it deeply troubling, because if every possibility happens, then nothing is unique. And if nothing is unique, how can we explain this, our particular arrangement of stars, atoms, and laws? Why do we exist here, and not in one of the countless other configurations? This is where the idea of the anthropic principle comes in. It says, we live in a universe compatible with life, because we're here to observe it. It sounds circular, it sounds unsatisfying, but it may be all we get. In a multiverse filled with randomness, the only universes with observers are those where observers can exist. So of course we find ourselves in one of those. It doesn't mean our universe was designed. It means we are the product of cosmic selection bias. But this raises another question. Can we ever know the multiverse exists? Can we detect other universes? After all, They're separated by inflation space, between us growing faster than any light signal could ever traverse. By definition, they're beyond our horizon. But maybe not entirely. Some researchers have suggested that if two bubble universes collided in their early moments, if their expanding edges brushed, the impact would leave a scar, a circle in the cosmic microwave background, a fingerprint from another reality. We've looked, and while we've seen hints, nothing conclusive, just echoes, just possibilities, and maybe that's all we'll ever have. But even without proof, the idea reshapes us. It forces us to think differently about existence, to imagine a reality where everything that can be is, where copies of you exist elsewhere, living different lives, loving different people, regretting different choices. A reality where this universe is not the answer, but just one answer in a sea of infinite questions. And yet, even in this boundless view, there's something profoundly grounding, because if the multiverse is real, then your existence, improbable as it may seem, is not alone. Your consciousness, your story, your soul are part of something larger than large, not by design, not by accident, but by the nature of reality itself. You are not insignificant. You are the consequence of a universe that allowed you to be, and that universe is just one ripple in an infinite ocean of becoming. There is, perhaps right now, a version of you wearing the same shirt, sitting in a similar room, watching this exact same video, feeling the same curiosity rising in your chest. A cosmic doppelganger, their atoms arranged the same way, their memories identical, their thoughts indistinguishable, but they are not you. They are a mirror, separated by an unfathomable stretch of space and an idea so vast it breaks the boundaries of reason. The infinite multiverse. The logic is simple, almost terrifyingly so. If space is infinite, and if the number of ways matter can arrange itself is finite, even if unimaginably large, then eventually patterns must repeat. Not just similar planets or galaxies, similar people, you, again and again and again, not just once, not twice, but countless times, identical versions of you, living out this exact moment, imperfect copies, where you wore a different color shirt, radical copies, where your life took a different turn at age 9 and you never looked back. This is not fantasy. It's mathematics. It's probability in a space where probabilities are endless. How does this happen? The answer lies in quantum fields, eternal inflation, and the idea that the laws of physics, while constant in their behavior, allow for limited arrangements of particles within any finite region. Think of it like shuffling a deck of cards. There are 52 cards. The number of possible arrangements is huge, 8 times 10 to the power of 67, but it's not infinite. So if you keep shuffling forever, eventually, the exact same deck will reappear. Now apply that logic to universes. If there are only so many ways particles can be arranged, even if it's 10 weave-cuz-2, 10 guz-cuz-2, and if there are infinite regions of space, then eventually, your exact arrangement of particles must happen again and again. Somewhere out there, another Earth orbits another sun. It has your name, your dog, your family, your memories, but at some point, your paths diverge, a different choice, a different accident, a different dream followed or forgotten, and from that fork, another life unfolds. There are versions of you who became poets, versions who never learned to read, versions who never survived childhood, versions who lived to be one. Ling, ach Universe, a canvas, each you, a brush stroke. Together, they form a gallery that you, the real you, the only you you'll ever be, can never see. Let that disturb you. Let it shake something loose, because if every possible version of you exists, then what makes you, you? Are you the sum of your choices? But what if every possible choice has been made? Are you unique? But what if uniqueness is an illusion, and your precise configuration exists a trillion times across the cosmos? Are you free, or are you just the inevitable consequence of physics, probability, and space? Some find this vision horrifying, a cosmic erasure of identity, a blurring of the self into statistical fog, but others find it beautiful, because in a multiverse of infinite selves, this one still matters. This life, this thread you're living still holds meaning. It is your window into the vast, your singular perspective in a sea of possibilities. Even if there are other versions of you out there, only you get to see through these eyes. Only you get to feel this exact moment. You are one instrument in an infinite orchestra playing your part right now, and this has implications far beyond science. If other versions of you have failed, then you can succeed. If other versions of you never healed, then you can. If other versions of you never asked the big questions, then this version you, here, listening to this story is the one that does. You may be one of many, but you are still one. Some theories go even further. They say the multiverse isn't just a result of infinite space, but of quantum branching, that every decision you make splits the universe into branches. In one, you turn left. In another, you turn right. In one, you say yes. In another, you walk away. Reality, splitting endlessly, branching like a tree that grows new limbs with every heartbeat. If true, then your mind, your consciousness is a thread weaving through this fractal, and what you choose becomes everything. But let's return to scale. The multiverse is not near. It's not a parallel Earth behind the moon. It's unimaginably distant, separated by space expanding faster than light, and by probabilities so extreme they defy intuition. There's no way to visit these other selves. No message can be sent. No contact can be made. They are ghosts, mathematical phantoms, reflections in an endless mirror room, and yet their existence reframes everything. It reframes loneliness. You are not alone. You are an echo in a choir of selves. It reframes meaning. This moment matters precisely because it will never come again. Not in this form, not in this world line, and it reframes the universe itself, not as a place of one story, but as a library of all stories, a library so vast, so full of life and loss and wonder, that even eternity may not be long enough to read them all. So here you are, in one branch, in one bubble, in one universe, and maybe that's enough, because infinity doesn't diminish you, it illuminates you. You are a single thread of possibility stretched across the grand cosmic loom, and your existence, brief as it may be, is still miraculous. Even if you are one of many, you are still you. The multiverse is grand, elegant, seductive. It explains much. It frames our cosmos within something larger, something that removes the sting of fine-tuning and makes space for all possible realities. But behind the awe comes a whisper. Can we ever prove it? And if we can't, is it science or is it myth dressed in math? Science is built on a sacred pillar, falsifiability. A theory must make predictions. Those predictions must be testable. If an idea cannot, in principle, be proven wrong, then it's not science. It's philosophy, or putri, or belief. So where does that leave the multiverse? The challenge is profound, because by definition, these other universes are separated from us by inflating space, expanding faster than the speed of light, isolating each bubble forever. No ship can reach them. No signal can pass between them. No telescope, however divine, can peer across that endless divide. But maybe, just maybe, there are scars. If two bubble universes collided in their early stages, the impact might leave a mark, a circle, a ripple, a pattern in the cosmic microwave background. Scientists have looked, they've scoured the sky, mapped its faint radiation, hunted for clues in the afterglow of creation, and what they've found is Nothing definitive. Some patterns, some hints, but nothing that rises above coincidence. Nothing that survives deeper scrutiny. It's not disproof, but it's not confirmation either, so we sit at the edge of knowability. The multiverse, while deeply grounded in modern physics, while emerging naturally from inflationary models, remains frustratingly untestable. It might be real, it might be the deepest truth of all, but it's a truth locked behind a cosmic firewall, and even the physicists who first birthed these ideas are divided. Paul Steinhardt, one of the architects of eternal inflation, has become a fierce critic of it, not because the math is wrong, but because the implications are too loose. In a multiverse where everything happens, how can you predict anything? If every outcome occurs somewhere, then your specific outcome, no matter how rare, tells you nothing. It's like flipping a coin an infinite number of times and asking what the last toss tells you. You lose explanatory power, you lose predictive strength, and in science, those are everything. Others, like Leonard Susskind and Andre Linde, argue the opposite. They see the multiverse not as a failure of science, but as its next frontier. They argue that even if we can't observe other universes directly, we can test the theories that predict them. If inflation is proven to be true, and if eternal inflation is an inevitable feature of inflation, then the multiverse becomes a consequence we must accept, not because we see it, but because the math demands it. It's a subtle shift from proving the existence of other universes to proving the mechanism that must create them, and that, perhaps, is enough. Just as we infer black holes from the motion of stars, just as we accept dark matter from the bending of light, we may one day accept the multiverse not as observed truth, but as inferred necessity. But here's the danger: when we step too far into untestable terrain, we risk drifting into metaphysics. We begin to build castles in the sky, mathematical palaces that may be beautiful but empty. We begin to worship the elegance of equations rather than the harsh discipline of experiment. We may find ourselves in love with theories that can explain everything but predict nothing, and that is a seductive trap, because science is not imagination. It is constrained imagination, bounded by nature, tested by reality, tempered by failure. So what do? Do we reject the multiverse until it's measurable? Or do we accept it as a necessary step in the evolution of our understanding? Maybe the answer is not binary. Maybe the multiverse is not a theory to prove or disprove, but a lens, a way of thinking, a shift in scale, a reframing of possibility. And maybe, just maybe, that's enough. After all, there are many ideas in science that began as whispers. Black holes were once thought absurd. Quantum mechanics was once ridiculed. The Big Bang was once dismissed as mysticism, and now they are part of the fabric of our understanding. So too, perhaps, with the multiverse, not because we will one day see another universe in a telescope, but because it helps us make sense of the one we do see. It helps explain why the constants of nature seem tuned for life. It helps explain the origin of space and time. It helps illuminate the strange dance between probability, possibility, and being. It might never be testable, but it might still be useful. And what about us? What does it say about humanity? That we dream of other realities and then try to prove them? That we stretch our minds beyond what we can touch? That we ask questions we know may not have answers? That we imagine infinity, not as fantasy, but as science? Perhaps that is our greatest strength, not that we can measure everything, but that we are bold enough to try. So we stand, once again, at the edge of knowledge, of science, of story. Beyond us may lie an infinite sea of universes unreachable, unknowable, real, and though we may never touch them, we still reach, because that's what we do. We look into the dark and try to find the truth. What if everything you've ever seen, every atom, every star, every galaxy, isn't made of particles? What if, at the deepest level of reality, there are no dots, only vibrations? What if the universe isn't a machine, but a musical instrument, and everything in existence is a note being played on it? Welcome to string theory, the most ambitious, elegant, and confounding theory in the history of physics. A theory that doesn't just try to describe reality, it tries to explain all of it. At the heart of string theory is a radical idea. The fundamental building blocks of nature are not point-like particles, but tiny, vibrating loops of energy strings. Each string has tension. Each string can vibrate in countless ways, and each vibration gives rise to a different particle, like the strings on a violin. Different modes create different sounds, or in this case, different fields of nature: electrons, quarks, photons, even gravity itself. So instead of separate building blocks for every force and particle, string theory offers one unifying idea. Everything is made of the same thing, vibrating differently. But there's a catch. For the math to work, strings can't exist in the 3 dimensions of space. We know they need more room. String theory requires extra dimensions, not just 3, but 10, or even 11. If you include time, where are these extra dimensions? We don't see them. We don't walk through them. They are believed to be curled up, compactified into shapes so small, so tightly wound, that they're invisible to us. But they're not irrelevant, because how these dimensions are folded, knotted, and curved determines everything. Imagine a guitar neck carved into a million strange shapes. Each unique geometry changes how the strings vibrate. The same is true for the universe. The shape of the extra dimensions determines the vibrational possibilities of strings, and those vibrations determine the laws of physics, gravity, the speed of light, the mass of the electron, all emerge from this unseen geometry. This leads us to the string landscape, perhaps the most mind-bending idea in modern theoretical physics, because the extra dimensions can be curled in vastly many ways. Not dozens, not millions, but around 10 circumflex, 500 possible configurations. Each configuration leads to a different physics, a different universe, différents particles, different forces, different realities. This isn't just theory, it's baked into the mathematics of string theory. And if every configuration is allowed, and if eternal inflation creates new universes endlessly, then the multiverse becomes the physical realization of the string landscape. Each bubble universe, a different arrangement of string vibrations, each one a different point on the cosmic piano. But here's the problem. We don't know which arrangement our universe corresponds to. We don't know how to decode the shape of the extra dimensions we live in. We can't yet predict which set of string vibrations gives rise to our physics. We're staring at the keys of a cosmic keyboard, but we don't yet know the song it's playing. So why pursue it? Because if string theory is right, it may finally unify the 2 great pillars of physics: quantum mechanics, the theory of the very small, and general relativity, the theory of the very large. These 2 frameworks are breathtakingly successful, but fundamentally incompatible. String theory offers a bridge, a single theory where gravity and quantum mechanics arise together, not as separate ideas, but as different aspects of the same vibration. It even naturally includes gravitons, hypothetical particles of gravity, as just one more string vibration. It promises a theory of everything, a mathematical framework that doesn't just describe the universe, but explains why it must be the way it is. And yet, despite its beauty, string theory remains untested. We have found no extra dimensions, no string vibrations, no deviations from known physics that require it. Its predictions lie far beyond our current experiments. Its equations are too vast, too slippery, too abstract to resolve into concrete answers. As it stands, we cannot even say which version of string theory applies to our world, if any. It is a castle of logic, built on clouds, still, there's something magnetic about it, something poetic. String theory dares to imagine that the universe is not random, that its laws emerge not from accident, but from resonance. That reality is music played on a multi-dimensional harp, and that each universe in the multiverse, each bubble born of inflation, corresponds to a note in that infinite composition. But here's where it gets stranger still. If the landscape of string theory allows for every possible combination of physical laws, then maybe the question, why this universe, has no answer. Maybe it was never meant to. Maybe we live in this reality with this chemistry, this gravity, this light simply because we can. In all the other points on the string landscape, maybe no one is asking questions at all. This is the anthropic principle. Revisited, we live in a universe compatible with life because we are here to observe it. It doesn't explain why our universe is possible. It just explains why we're in this one. Some physicists hate this idea. It feels like surrender, like giving up on deeper explanations, but others argue that it's simply the way things are. In a cosmos of infinite variations, we find ourselves only where we can. So what does this mean for us? It means the laws of physics may not be universal. They may be local, bound to the shape of dimensions we can never see. It means the constants of nature, the speed of light, the strength of gravity are not written in stone, but in vibration. It means that all we are from breath to brain to being is the resonance of something deeper, something smaller, something beautiful. And if that's true, then the question we must ask isn't just what is the universe made of, but what is the universe trying to say? Our cosmos balances on the edge of a blade. Gravity is just strong enough to pull galaxies together, but not so strong that it crushes everything into black holes. The electromagnetic force binds atoms, but doesn't tear them apart. The mass of the electron is just right for chemistry. The cosmological constant, the energy of empty space, is shockingly small, allowing galaxies to form instead of tearing space asunder. If any one of these values were slightly different, we wouldn't be here. Not just you or me, but anything. No stars, no atoms, no time. The universe appears fine-tuned like a safe with 100 tumblers, all set just right. Why? It's one of the most profound and disturbing questions in physics. Because unlike other problems like dark matter or black holes, this isn't a question of missing particles. It's a question of why things are the way they are at all. Some say this is evidence of design, a creator who dialed the knobs of reality just right. Others say it's coincidence, a lucky cosmic accident. But in recent decades, a third idea has emerged. Maybe it's neither. Maybe it's necessity in disguise. This is where the string landscape and the multiverse come back into the story. We've seen that string theory allows for an unimaginable number of different universes, each with different configurations of space, time, particles, and forces 10 circumflex 500 or more. In that vastness, most universes are dead, too hot, too cold, too short-lived, too chaotic. No stars, no chemistry, no observers. But among the dead, some live, and we happen to be in one of those. This isn't mystical, it's statistical. The argument goes like this: if every possible universe exists, then some will have the conditions necessary for life, and observers can only exist in those universes. So it's no surprise that we find ourselves in one. It's not that the universe was made for us, it's that we could only appear in a universe like this. But this explanation comes with a price. It means we can't predict the values of fundamental constants. We can only say they're what they must be for observers to arise. This is the anthropic principle, sharpened into a scientific tool. Not everyone is comfortable with it. It feels like giving up. It replaces why with because otherwise we wouldn't be here. It closes a door that science was trying to open. Others see it differently. To them, this is not surrender, it's realism. If the string landscape is real, If the multiverse is vast, then the only universes that can ask why are the ones that are structured enough to ask. It's not teleology, it's selection bias. You don't marvel at winning the lottery if only winners can speak. But there's a problem. This logic is hard to test. How do you verify a theory that predicts every possibility? How do you falsify an idea that says, we're here because we're here? And yet, maybe we don't need to test every universe. Maybe we can explore the distribution. Some physicists are now trying to map the landscape to understand which combinations of constants are most common in string theory's vast possibility space. If the values in our universe turn out to be typical among life-permitting ones, then maybe the anthropic explanation is strengthened. But if they're extremely rare, even within the habitable set, then we're left, once again, with mystery. This brings us to the legend of the Gordian knot. In ancient Phrygia, a complex knot was tied around a sacred cart. It was said that whoever could untie it would rule all of Asia. No one could unravel it. Not until Alexander the Great arrived. He didn't study the knot. He didn't trace its loops. He drew his sword and cut through it. Some problems, he decided, weren't meant to be solved delicately. They demanded a bold, sweeping answer. The fine-tuning problem may be our modern Gordian knot, the tangled strands of constants and parameters and equations that just happen to permit our existence. And the sword we've raised is the multiverse, not because it explains everything, but because it makes the problem disappear. If every knot exists somewhere, then you don't need to untie this one. You just need to realize we were always going to be here. Wherever here happened to be, this is a radical shift. For centuries, physique so, a unique solution, one set of laws, one universe, one answer. But maybe the universe isn't a riddle to be solved. Maybe it's a branch on a cosmic tree. And our branch, while improbably, is not impossible. So what does that mean for us? Do we stop searching? Do we resign ourselves to the unknowable? No, because even if the multiverse is true, even if we are one of many, we still have work to do. We still have physics to explore. We still have equations to write, forces to unify, particles to understand, and perhaps one day we'll find that some values, some constants are indeed inevitable, baked into the logic of reality. Maybe the landscape isn't infinite. Maybe it's shaped. Maybe this universe, improbable as it seems, was the only possible one all along. Until then, the multiverse stands as both a sword and a mystery, a solution that unravels the knot but also hides the rope. We may never know if it's the right answer, but we know it changes the question. Time is the ghost we can't outrun. It whispers in every heartbeat. It presses into our skin. It loops our memories into a sequence and demands we call it life. But what if time is an illusion? What if the ticking clock we trust is just a trick of perspective? And at the deepest level, the universe doesn't tick at all? If the Big Bang is the beginning of time, then what came before? The truth may be stranger than any answer. It may be that the question itself doesn't make sense. We've been conditioned to imagine beginnings like stories. Page 1, Scene 1. The first spark, we ask, what came before the universe? But baked into that question is the assumption that time existed stretching back like a ruler, inviting us to inch along its past. But time isn't a ruler, it's a construct, and if the Big Bang marks the beginning of time, then before the Big Bang is like asking, what's north of the North Pole? There is no north, only the illusion that the map keeps going. This isn't metaphor, it's physics. In general relativity, time and space are woven into a fabric. Space-time must bends it. Light curves through it. But at the moment of the Big Bang, this fabric wasn't simply bent. It was born. There was no before, because there was no fabric on which before could rest. Time began when the universe began. Cause and effect only make sense after the first effect. And yet something still feels missing. Because we feel time, we move through it. We age in it. It rules us. Can it really be so easily dismissed? Here's where things get weird and beautiful. In quantum mechanics, time is treated as an external backdrop, a ticking parameter, a metronome that marks every fluctuation. But in general relativity, time is flexible relative. It stretches near gravity. It warps with velocity. It can even, in theory, loop. These two pillars of physics disagree on the very nature of time, and until we reconcile them, until we have a complete theory of quantum gravity, our understanding of time's beginning will remain fractured, like a puzzle with the last piece missing. Still, ideas have emerged, theoretical frameworks that try to replace the singularity, the supposed beginning point, with something deeper. In loop quantum gravity, space and time are quantized. They come in discrete units like pixels on a screen. You can't shrink the universe beyond the smallest unit of space or time, and when the universe collapses to that point, it bounces. No singularity, no beginning from nothing, just a rebound, a universe contracting, then reborn in expansion. Not a creation ex nihilo, but a cosmic heartbeat. Then there's conformal cyclic cosmology, proposed by Roger Penrose. In this model, time doesn't end or begin, it transforms. In the far, far future, when the universe becomes a cold, thin soup of radiation, with no matter left and no scale to measure time, that state becomes mathematically identical to the beginning of a new Big Bang. The end is the beginning. The arrow of time resets. The universe doesn't die, it renews. And there's more. In Brane cosmology, our universe is a membrane floating in higher dimensional space. Our Big Bang, a collision with another brane. Time didn't begin. It just reignited like flint striking steel. There was before, just not the kind of before we're used to. A pre-universe, a shadow realm, a cosmos with different rules, brushing against ours and lighting the fuse. These models vary. They contradict each other. None are proven, but they all point to the same thing: the singularity, the sharp, impossible point at the start of our equations is a signal not of truth, but of breakdown. Our math fails, our logic collapse. We stare into the edge of knowledge, and beyond it, we glimpse only questions. And yet, one idea pierces the fog. Time may not be fundamental. It may not be woven into the universe from the start. It may emerge like temperature or pressure from deeper laws, a statistical property of quantum systems. Some physicists suggest time is born from entanglement, the interconnectedness of particles in a quantum state. Others propose it's a consequence of information flow, like memory forming in reverse as entropy increases. In this view, the universe didn't begin in time. Time began within the universe, and before that, no sequence, no before or after, just a state, unchanging, timeless, waiting to wake. It's unsettling, because it suggests that time, the most intimate part of our experience, is not real in the way we think, that our past, our future, our clocks and calendars are projections of a deeper, stiller truth, that the flow of time is a story our minds tell, a narrative stitched by consciousness across a sea of quantum stillness. But even if time is emergent, we still ask the question. We still want to know what came before, and maybe that's the real message here, that we are time. We are the story that unfolds across the void. We are the observers that give meaning to succession, to causality, to becoming. So what came before the Big Bang? Maybe nothing, maybe another universe, maybe a collision, a bounce, a transition, a breath. But maybe, just maybe, the question is flawed, because before may not have meaning until there is someone to ask. Close your eyes. Now, try to imagine nothing, not empty space, not a vacuum, not a black void with stars too far away to see. Nothing, no space, no time, no atoms, no laws, no fields, no dimensions, no mind to witness it, no silence, even because silence requires time, and time isn't there. Can you picture it? You can't, because every image we conjure is something. The brain rebels. It fills the canvas. It paints black where there should be absence. It whispers empty when there should be non-existence. But here's the deeper puzzle. Despite our failure to imagine true nothingness, something exists. You, me, photons, planets, quarks and quantum foam. Reality is, and that is utterly baffling. Why is there something rather than nothing? It's not just a philosophical question. It's a scream from the edge of comprehension. Physics can describe how the universe evolved. It can write equations for gravity and energy and expansion. It can model the curvature of space and the jitter of quantum fields. But physics begins after existence. It assumes a stage, a blank canvas. It never explains why the canvas is there at all. Some argue nothing is unstable, that in the realm of quantum mechanics, even a vacuum bubbles with fluctuations. Particles pop in and out of being, so perhaps our universe tunneled into existence like a spark from the void. But even that model presumes something. A field, a vacuum state, laws that govern what tunneling means. It's not nothing. It's a strange something masquerading as nothing. The question remains. Others suggest that the universe is the ultimate free lunch, that the total energy of the cosmos is zero positive matter energy balanced by negative gravitational energy. If the net is zero, then maybe it's not so strange that a universe popped out. But again, this frames it after the fact. It doesn't answer why the laws of physics exist to allow this trick. Why is there a ledger at all? Why is there a rulebook for how nothing can give rise to something? Some reach for theology, a creator, a necessary being, a consciousness outside time and space who willed the universe into being. But then the question rebounds. Why God rather than nothing? Why any being? Why any will? Why anything? The mystery doesn't go away. It just moves upstream. There is a possibility terrifying, beautiful, that we may never know, not because we're not clever enough, but because the question itself has no answer. That why is there something rather than nothing is a malformed question like dividing by zero. That nothing is not a valid state. That something is the only game in town. That existence is not the anomaly non-existence is. Or perhaps nothingness is impossible. Mathematician and physicist Max Tegmark once proposed a radical idea that all possible mathematical structures exist, and that our universe is simply one such structure. That reality is math made manifest. In that view, existence is not rare, it's inevitable, because anything that can exist, mathematically, must. The ultimate multiverse, everything exists, every logical form, every possible reality, including ours. Others speculate that consciousness itself plays a role, that without observers, existence is meaningless or undefined, that the universe awakens through us, and so the question, why something, is deeply entangled with why you. If consciousness is fundamental, if awareness is not the byproduct, but the source, then maybe the answer lies not outside, but within, not in equations, but in experience. Still, we may be left with mystery, and maybe that's okay. Maybe the role of science is not to kill wonder, but to deepen it, to let us stand in the presence of the unknown. Not with fear, but with reverence. We have traveled from the edge of the universe to the edge of time. We've questioned beginnings and danced with infinities. We've watched space twist and time dissolve and logic bend, and still, the most powerful question remains the simplest. Why is there anything at all? There may never be an answer, and perhaps that is the greatest gift, because in that mystery, we find freedom to wonder, to explore, to imagine, to become. Existence isn't owed. It's a miracle, one we live inside. So the next time you look up, at the stars, at the black sky between them, at the silence that echoes through space, remember that it could have been nothing, but it wasn't. It is, and so are you. What you do with that is the final mystery.